Welcome back to the series on real analysis. Today we'll be going over some consequences of the axiom of completeness, which is more like the density of the rational numbers, going into the nested interval theorem, proving some things about that, and then talking about the existence of square roots. So let's start with the existence of square roots because that one took some thought, and I want to share the end of the theorem for that specific one. Let's begin with the existence of square roots. And this begins with a proof that the supremum of t, which is for every t squared less than 2, that this is equal to the square root of 2, that this supremum is equal to the square root of 2. This is proved by contradiction, and they show this by saying that if alpha squared is less than 2, or if alpha squared is greater than 2, then there will be a number in between alpha squared and 2 that contradicts that alpha is the supremum. And you can see, so the beginning of this proof gives the alpha squared is less than 2 here. And as a homework assignment, they gave us the option to finish the proof. And that's what I'm going to do here. So I'm going to take what they started with here and then walk through how to finish proving this statement. So let me present you with the proof. We're going to start quite literally where the book leaves off. So this is the expression that we're given, and we want to show that if alpha squared is greater than 2, it leads to a contradiction, that alpha can't be the supremum. So to demonstrate this, if we do alpha minus 1 over n, that will bring us closer to 2, given this assumption. And this expression here is bounded by this. So I found a choice of 1 over n that is bounded by this. And if you want to know how I got this, I can show you. Let me know. But I feel like the way to get better at math is to fill in the gaps. And finding this out is not very difficult. This is more algebraic expression. And then this implies this. So this is important because I need to know what this is bounded by. And some algebra will show that negative 2 alpha over n0 is greater than 2 minus alpha squared. And so then if we plug this in, so if we go alpha minus 1 over n squared is greater than this guy, which is greater than 2, which is what we showed by substitution. So this guy, remember, is greater than 2 minus alpha squared, which implies that this is greater than 2. So if we subtract some arbitrarily small number, then this will be greater than 2, and that implies that alpha is not a supremum. Because if you recall, if we were to subtract this guy by any number, any epsilon, then that would mean that this would be a supremum. I'll show you this lemma to hit this point home. All right, here's the lemma. So here we can see that if S is a supremum, then for every choice of epsilon greater than 0, S minus epsilon will be within A. So S minus epsilon will be less than A, where A is an element of our set. And in our case, we have this subtraction, but our upper bound is 2. And despite this subtraction, we are not inside our set. That's why this is a contradiction. Our next two proofs are just some problems that I thought were fun in the book. So let's go through these now. I chose this one because I think this proof is interesting, and it might be wrong, and I'd like to know your thoughts. Okay, so let A be some subset of the real number line, and let it be non-empty and bounded above, where S is an element of R. It has a property that for all natural numbers, if we were to select one just incrementally, S plus 1 over n is an upper bound for A, and S minus 1 over n is not an upper bound for A. So we have to show that S is the supremum. Let me walk you through that proof. So let's look at S minus 1 over n. This is not an upper bound for A. We know that because that's stated in the original problem. Then for all n, we have this relationship because it's not an upper bound. So because it's not an upper bound, we know that this inequality is true, where A is an element of A. But we know by the Archimedean property that 1 over n is less than epsilon. And so for all epsilon greater than 0, given that epsilon is an element of a real number, or is a real number, this implies that s minus epsilon is less than s minus 1 over n is less than s minus epsilon because of this Archimedean property. And then that is less than a because s is a supremum. And so this follows by the same thing that we showed previously, that if we have some subtraction where this inequality is true, it implies that s is the supremum. And I'm having a problem with this because the problem gave me more information than I used, and that always makes me nervous for a math problem. So let me know what you think about this proof, because I'm skeptical just because I didn't use all the information, but I could just be paranoid from other stuff. Okay. So the last problem I want to go over is proving that the infinite intersection of 0 and 1 over n is empty. And I want to do this because this one is slightly different from the nested interval problem, where that problem has closed sets. So let me show you that. So here is the nested interval property, where if each interval is contained within the next one, so I1 is the big one, I2 is contained in I1, and so on and so forth, then that means that the interval is not empty. And the point of, the crux of this argument here is that we have the supremum, and the supremum is in the set. And so that's why it's not empty. And I think the problem I showed you is instructive because the intervals are open, and we can see why or when this theorem falls apart. So let's go into that proof. Okay, so we want to prove that this set is the empty set. And so I drew a picture here so you can see that as time goes on, these guys get smaller and the set eventually converges to 0. So we let a equal 1 over n, where n is some natural number. So a is just the sets that sort of get smaller, or the upper bounds of the sets that get smaller. And so it can be observed that the infimum of this set is 0. And because 0 is not in our set, it implies that this is the empty set. And the most important part here is that the infimum is not in the set. Because if it was, that would be included, and the intersection would not be empty. Thanks for watching. Remember, I'm not a mathematician, so if there's a problem with any of these proofs, let me know in the comments. We can have a conversation about it, and I'll see you guys next time.